Hello, my name is David Ackerman, student number 220310629, and this is the Mechanics 2302 assignment for dynamics, assignment 3. Let's get started. So this is the question where it has part A with a diagram and then part B, which is written response. So based on the question that was given, the omega AB is 4 rads per second. The length of AB is 500 millimeters, which converts to zero point 0.5 meters. The length of CB equals 350 millimeters, which equals to 0.35 meters. The angle for A is 60 degrees, the angle for C is 45, and for the problem, we're trying to find the velocity at C and omega CB. So let's get started. So before we begin, these are the schematics slash the free body diagrams with all the known informations and of course with the missing values because we're going to fill them in with the calculations. So we're trying to find out for the angular velocity at C and the length CB. So we use the formula velocity B equals velocity A plus omega AB times the radius of AB. So velocity A is originally 0 meters per second plus the 4 rads per second that were given times the radius of AB, which is length AB, which is this value right here. And we get that velocity B equals to 0.2 meters per second, which equals to velocity A. And so here we're trying to find the radius. So RIC over C divided by 60 sine 60 equals 0.35 meters over sine 75. We isolate it and we find that RIC over C equals 0.3138 meters. Here we're just setting up some ratios to find that value. We do the exact same thing here where RIC over B, we find that that value equals to 0.2562 meters. And these are just ratios that we find. So now to find the value for the angular velocity of BC, we use that velocity of B equals um, the omega BC times the RIC over B, and we isolate for omega BC, and we can actually use that because we have both values for B and right here. And we get that omega BC plugging in all the known values equals 7.81 around. And we do the exact same thing, but with C and velocity C, and we actually don't isolate it because we're trying to find velocity at C. We plug in all the values with RBC and then the RIC over B, and we get that the velocity equals 2.4496. So therefore, the velocity at C equals 2.45 meters per second, and the angular velocity at CB equals 7.81 rads per second, rounded. So part B, we're trying to um, slow down point C so we can modify the system in these following ways. So part one is to reduce the angular velocity at B since VC depends on the angular velocity of AB. This would directly slow down the effect at the door. The solution would slower calculator at point A with a variable speed moderator. The effect reduces the overall speed of the system. So increase the length of the link CB. What this would cause the CB value means that the slower angular velocity, because it has to maintain the same velocity, meaning that the slower angular velocity would be conducted in here. Omega CB reducing velocity at C, and the solution would increase CB's length for 0.35 to a larger value, and the door would move more slowly and smoothly. And lastly, the third option would be adding a dampening or soft closing mechanism. The dampener slows down the motion of the door approaches, meaning a hydraulic damper, something that would slow down the motion more consistently. This would prevent sudden stops, reduce friction, and then ensure a more smooth operation with less hiccups. So the best recommendation out of these three would be a combination of reducing omega AB, increasing the CB's length, and adding a dampening will make the system more safer and more accessible to wheelchair users, meaning that if these were incremented or implemented in the system, incrementally implement in the system, it would cause to be safer for the desired users. This is my video. Thank you so much for watching.